Hello everyone and welcome back to another little video on dealing with parametric functions in Calculus 2. This time around I'm looking to show you how to integrate parametric functions, and I'm going to show you how to derive basically the way to do it by looking simply at normal Cartesian coordinate functions, so a y of x and how to integrate that. And then we're going to build up using implicit differentiation, how to do it for parametric functions, which is not going to be that bad. So let's pretend over here that you have a regular function y of x, and it goes like this. And you decide that you'd like to find again the area beneath it between two coordinates here of x. We'll call them x1 and x2. So you're looking to find again this area right here. We know that if your function again is described as y of x, we can do that by using an integral. And that integral would be integrating your function y of x with respect to x between those two endpoints. That's what we know. So how do things differ when we switch into the parametrized world? Well, in the parametrized world, basically y changes character because x becomes defined with respect to a parameter called t. And this immediately, you see, if I plug this back to y, this immediately gives rise to y being a function of t at the end of the day. And so immediately here, in our list of changes, the y of x will change to a y of t. That's the first thing that will happen. So what do we do next? What happens with the dx right now? The dx can be taken care of simply by recalling how we used, like the little trick that we use for implicit differentiation. So for example, when I wanted to take the derivative of this, and I wanted to, I wanted to use implicit differentiation, I basically did this instead. And the idea was that these will communicate, and technically these cancel to give you back the original derivative that you had all along. So using this little trick right now, I can describe dx secretly. I can replace it with dt, but that wasn't there in the beginning. So how can I make it so that dx is there after everything, kind of cancels and is said and done? I can do so by multiplying by a ratio here, simply of dx over dt. As you can see, that would cancel with the dt that is outside, and we get back the original definition. Now, when we're doing this, we're technically now officially in the t world, and our parameter would run from some value, again, t1, all the way to t2. And that's the way we switch the integral, really, to do parametric functions. It really is not that complicated once you get used to it. So we need to put in what y is in terms of t, and then we need to differentiate the function of x with respect to t, and then we carry our integral as normal. So I'll take that, and I'll show you how simple it is to apply it in a problem you'll typically see in an assignment that looks somewhat like this. So this is tasking us to find the area under the following parametrically defined curve, and it gives us the indicated interval for t. So again, I need to fill this up. So let's see. Y of t is simply t right now, and x of t is 1/4 t to the 4th. So if I want to find dx dt, I simply have to differentiate this with respect to t. And of course, that's going to get me 4 over 4t cubed, or simply just t cubed right now. So, plugging all the pieces then inside my area integral, I know I'm integrating between 0 and 1. That's what they've indicated that they want me to do. I know that my y of t is simply defined as t. And I know that my derivative right now of x with respect to t came out to be t cubed. So I plug that in as well. And then I take the integral as I would normally. So the result here of this integral is very simple. We're just integrating t to the fourth with respect to t from 0 to 1. This comes out to be t to the fifth over 5 from 0 to 1. And then if I plug the endpoints here, I'll pull the 1/5 outside before I plug in the endpoints right now. So t to the fifth, we have 1 to the fifth minus 0 to the fifth. And that leaves us with an area of 1/5. So this is the premise. And any function that you have defined your x and y to be in terms of will work the same way. All you have to remember is, again, the form of the integral, what you need to plug in it. And if you don't remember it, again, I showed you that it's very, very simple, actually, to define it from the Cartesian equivalent by doing a couple of subtle changes, turning this into a y of t as x obtains a t dependency, and then using a little bit of implicit differentiation to express this in terms of dt instead. Everything else is very straightforward. So I'll leave you with this. I hope, again, this video was helpful in how to integrate parametric functions. If it was, consider subscribing.